Hello kids, today we will be reviewing 5th unit of IGCSE 065 Physics, that is forces and matter, how forces are going to interact with matter. Previously we were discussing forces and its effect in terms of the motion of the objects. So today we will be discussing not the motion but instead how it will affect the dimensions or uh, how it will deform matter, right? So we do understand that whenever we apply a force on an object, it moves, right? It accelerates under the action of a force. That is what we had to consider in F is equal to ma. But that's not what we will be discussing in this unit. So instead, we will be reviewing something else. We will understand how forces will act on objects which are fixed. For example, I have this wall, right? And from that wall we actually have this steel bar, and if I apply force over here, I would see that the bar would tend to bend, right? So that is what we call as a bending force, right? The bending effect of a force. Similar way, we have several other ways in which a force can act. For example, I have an object, right? And I pull that from both these sides, right? Force is applied, so this will elongate uh, the object, and the cross section will reduce under the action of the force. This is what we call as tensile load, right? Now we will consider forces in terms of loads, right? How a load or the loading effect of a force is going to be there. So this is what we call as bending. It is now bending matter, and in this case it is once we pull it on both the ends, it is what we call as stretching, uh, right? And stretching, or what I call as tensile loading, and the other way around is compression, right? For example, I have another uh, piece, and I just apply forces in the opposite direction to the tensile load, and we would find that the object is now compressed. It's widened out, the cross-sectional area will increase, but it will actually become more less in reduce, you can say reduced in height and more in the cross-sectional area. This is what we call as compression, right? uh, and lastly, we will understand that what if the object, for example, it is fixed. Let's say if we have a square, I apply force just on the top of this, right? So I would find that the object is now twisted like this. Now this is what we call as shear force, right? Shearing. And lastly, we will be reviewing torsion. For example, if I have a rod and I fix one end of it, right? I just fix it up and I apply torque or a moment, a force that is going to generate a moment. So I would find that this pipe will be twisted, right? This twisting effect is what we call as torsion, right? That is the word that is also coming from the word torque. So this twisting effect is there. So in general, we can say that our uh, there we have you can say stretching, right? The stretching effect, number one. Number two, we have compression. Number three, we have bending. Number four, we have torsion. And number five, we have shearing, right? Now we do understand that we use the word shears for a pair of scissors, right? And what it does, it actually cuts the material just by shearing, just like that, right? One part of the scissor is pulling it this way, the other is pulling it this way, so the material is going to be cut from somewhere in the middle, right? That is what that's how a scissor is operating, right? It's a shear, so it applies shearing forces to cut the object. So this is just the basic idea of how forces act on the matter. And you know, another thing is there, which is which is flexural strength, but that is actually also known as the bending strength. So bending can also take place. For example, if I have a rod, I apply a force from the middle and two forces on these ends, then I'm going to see you know, kind of a bending effect, right? This is also another case for bending. I used a fixed object previously, but this is also bending, right? So remember these images, that these forces are the direction of the forces create different types of loading conditions from matter, in which we have namely stretching, uh, compression, bending, torsion, and shearing. Shearing is actually not much discussed in IGCSE, but these four are actually there, and you need to be able to differentiate them in terms of their application, the way force is going to create these you know, loads. This is a rotational load, this is a shearing load, this is a compression load, this is a tensile load, and it's a bending load, right? So you can call that the you know, forces which are creating these loads on matter, right? Now that's the basic idea of this unit. Now we're going to go into a deeper and more detailed topic in this section, which is the elastic force, right? And what is elastic force? As I just gave you the example, let's say if we have a piece of uh, metal, right, and we stretch it on both ends, and once we do stretch this, we're going to see that the cross section will reduce, right? There will be some extension. As you can see, there is a change uh, in length, right? And that is due to the action of the force. So this is what we call as extension due to load, right? Due to load or force, right? Either way it works. Now we call this kind of effect, this effect, as the stress generated by a force. For example, if I uh, if if I have a sticky man, right, and I ask two more people to pull him up, you know, this way, another one pulling him this way, right, and you will find that this man, this person in the middle, is going to be stressed out. Why? Because he's being pulled on the opposite ends, he's being stretched. So this is under stress, right? And these are loads, you can say load on this side and load on this side. So this object in the middle, or this person in the middle, is going to be stressed out. So we will say that the extension that this person is going to experience is due to this stress generated by these loads or forces, right? So we can also call this as force. uh, yeah, right. So let's now get into more technical detail of this topic. So what is elastic force, right? This is since things are being you can say stretched out, we can say this is also known as elastic force, right? The force which causes these extensions are called elastic forces, or an elastic load, right? And why? Because once we release this force, the object is supposed to get back to its original position, right? And that is what we call as Hooke's law, right? So to understand elastic force, we need to first acquaint ourselves with this Hooke's law. And the Hooke's law states, I'm just going to draw a graph, right? Uh, Hooke's law states, let's say this is load, and this is extension, right? And this could be in centimeters, millimeters, and the load could be in newtons, right? This could be in newtons, this could be in millimeters, right? Because things do not actually tend to extend that much. I've exaggerated the example over here, that it is being stretched out, but that's not how it works. So I'm just going to draw the example again. Here's our sample, right? and we're stretching it out, we're trying to extend it, and there is some extension in the object, right? And that extension is temporary as long as the forces are within certain limit. And what is that limit? That is what we call as the Hooke's law limitation, right? And in that case, if we increase the load uh, gradually, uh, the extension will be there, right? To a certain point, this is what we call as uh, limitation, right? This is the limit, and this is what we call as elastic limit, right? And what is an elastic limit? It's the limit to which this object can extend, and once we remove the force, it will get back to its original condition, right? And if uh, we exceed the force or exceed the load more than this, then we will see that under less force there is a lot of extension, and a point will come that the object will fracture or break, right? So this is the fracture point or breaking point. At this point, this rod, now I'm just going to extend it. Let's say we extended it too much, and it would just uh, tear apart, right, into two pieces like this. So this is when the fracture limit occurred. So we can say this is the elastic limit, right? Uh, Elastic limit. And what is elastic limit? If we remove the forces, it should get back to its original position, right? We can say this is L naught, which is the length, original length, and this is the L E extended length, right? So once we remove the forces, these stretching forces, the object should get back. And if we go past this limit, then there is a permanent defect in the object, and the object will not be able to get back. Let's say if I keep stretching it up to a point that it won't be and I'm going to call this as LP. This is the permanent change in the length. Now the object is no more able to revert back to its original position. This, however, will, right? So this is the elastic limit. I'm just going to draw a line that this, beyond this, is the elastic limit. So uh, uh, if we let this object retain back, and it will turn back to a certain position, right? So there will be a certain change. This is permanent defect, right? This is the permanent change that has occurred now. The example would be you take up a piece of plastic or a shopping bag, right? Any plastic bag, you just stretch it a little bit, and you would find that it does not change, right? It reverts back. For example, if you take a rubber band, if you pull it apart, if you stretch it, it can get back to its original position. That's why rubber bands have a very good elastic limit. But if you elongate it too much, it would fracture. But in the case of plastic, if you stretch it a little bit more than its limit, you would find that there's a permanent change now. And if you remove the force before fracturing it, there will be a permanent increase in length of that plastic sheet or plastic material, right? Now that is what we call as a permanent extension or permanent defect in the object, right? Now moving on, let's try and chart some values and see how an object is going to behave under special or specific conditions. So what is Hooke's law? It is this linearity, right? So the linear behavior of an object or sample under stress or load, I will call it stress, right? Uh, for load to extension graph, right, is Hooke's law, right? That if, as long as the forces, if I, let's say if I pull up an object, I pull it to this point, it should get back to its original position right here. It would get back to original position. without having any issues. But if I go beyond this point, then it won't be able to get back to its original position. It would have a permanent defect, and if I keep on increasing, a point will come that it would fracture, which is this case, right? So we can simply say that the elastic limit is to be followed. After that, there's a permanent change, right? So that is what Hooke's law is all about. We can now relate an example, which is an everyday example. You can do this at home. For example, you take out, you have those clicking ball pens, right? Take out a spring out of that ball pen and try and do what I'm just going to do, right? So if you pull this spring, you would find that at a certain value, right? This is A, this is B. So you would find that the spring is stretched a little bit, right? Under the action of the force, which is downward. But if you release it, it would get back to its original condition, right? Just like A. But this was extension X, right? Displacement. Contrary to this, if I now again stretch it up to a point that I go a little too hard on the spring, right? Under the action of the force. Over here there is no force, right? No force. So it came back to original condition. So that's the Hooke's limit, right? Hooke's law, the linearity. After this, in terms of D, if I pull it too hard and if I go beyond the elastic limit, I would find that now the spring is permanently defected, right? It won't be able to get back to its original position. Let's call it Y. So we call this permanent change, and that is above Hooke's law. And in this case, we can easily see that the more the force I apply, the more the extension is there. So I can say that F is proportional to X, which is the extension. Over here, F is applied force or load, and X is extension to original length, right? Now what if I go beyond, I need to understand that something, if I you need to understand, in this case I'm just going to draw a graph first, and then I'm going to help you understand what is happening over here, right? I'm just going to draw a rough graph over here. Let me just change the color. Okay, this was extension, right? And this was the load or the force. There was for point A to B, that is, let's say this is A, which is the original point, and this is B when it was stretched. C is going to be also over here at the same point, right? But D is going to be here, right, till D point, and since D is there, then E is going to be somewhere here. So that is going to be point E on the graph, right? So I've differentiated these points just to show you what is really going to happen, the permanent defect compared to this original length, which was L naught, right? So again, let me just do this. Yeah, this is L naught and the extension that was there, and it came back to L naught, right? No changes. But in this case, again, I'm just going to mark L naught, and this is extension Y, right? I'm just going to replace this Y. I wrote Y just to differentiate this, but now I'm going to write X because I'm going to drive the formula. I will find that there is permanent change in X over this L naught, and the object is no more able to get back to its original position with the absence of force, right? No force here, right? Again, but not original, right? So that's what the Hooke's law is suggesting you, that it will have a permanent extension once the force is removed. Now, once I pull it down, in this case, let's say in case B and C, when I pulled the spring and I left it without the force, it somehow got back, right? And what did it make it go back? And that's what we call as the elastic force of the spring. So we will say that the spring will return to original condition under action of elastic force, and which is equal to applied force considering elastic limit is not reached, right? If we don't breach the elastic limit, then we can say that the applied elastic force, or what I will now call as Fe, should be equal to the applied force, and that is going to cause this extension. And in this case, it is going to be minus F. I'm going to use this negative sign for the force. Why? Because the elastic force, as you can see over here, what I'm going to say, Fe is actually opposite to the applied force, right? I'm just going to highlight this using this color pencil, that this is the direction of one force and this is the reaction. Now here Newton's third law will again be applied, that to every force there is an equal and opposite reaction. So that is what you are having over here. This is the equal and opposite reaction. Third law of Newton, right? Action to reaction, that's what is being witnessed over here. And we need to understand that let's say if I have a larger spring or a thicker spring, let's just say we have spring 1 over here like this, and the other spring is actually kind of made out of a little larger or a thicker material. Which one do you think is going to extend more? And my bet is on this one. Under the action of same force, if the same force is applied to both of them, I would find that this thin one is going to extend more than this thicker one. So there is something which plays part in the extension. It's a factor known as Springs constant or elastic constant, right? Elastic constant or spring constant. For in case of springs we call it spring constant, and that is represented by this letter K. So over here I can say that F minus E is equal to K into X. That means the more the factor, this K is actually a representative of the number of turns that are there and the thickness of this spring. So many factors affect the material as well. Different materials tend to have different values for K. So I'm not going to go into detail of how we get the K, but I'm just going to give you a brief that this K depends on thickness, turns, how many turns are there, and the material, right? I'm just going to hint it out for you. Although these factors are not asked in IGCSE, you just need to understand that this Springs constant is the cause which will make the spring go back into its original position, right? So this is the summary of Hooke's law, and let's say if I give you a certain value for K, we need to understand that how much extension is going to be there for different springs. It is going to have different extensions under the same force. If force is same, then different springs will have different level of extensions depending upon the material that is being used, or the number of turns that are there, or the thickness that is there, right? I hope I've clarified the concept of how Hooke's law works and what is elastic force. Now we're getting into the last idea, or the last topic of this unit, which is pressure, right? Now I'm keeping this topic a little short because we don't need to go into much of the details, since some of these topics have been removed for the year 23 to 25 syllabi. So we're not going to go into much detail which was previously available in the books. Now it has been removed, so we're just going to keep it short. Uh, Now, what is pressure, right? What is pressure? Pressure is when we say that something is being applied on a certain area. Let's just say we have a certain area and we apply a certain force, and that force is acting on a certain area, so that effect of the force will be distributed across this area. Now imagine, let's just say I apply a force of 10 newtons on an area which is 1 meter square, compared to another area which is half of it, right? 0.5 meters square, let's say a smaller area. Now which one do you think is going to receive more pressure from the force, right? Which one is going to have more effect of the force? Considering that the force applied is same, so this case will have more pressure, right? And why? Because the area will definitely come into effect. The smaller the area, the more the force. The bigger the area, the lesser the effect of the force. So we can simply say that the pressure applied on a certain area is directly proportional to the applied force. Let's say if I hold your finger and press it down with just my pen, that is going to be very, very excruciating for you, because the area of the pen is very small, and even little force is going to be very, very devastating for you. But what if I put your finger and push it down using a notebook? Then it's not going to have much of an excruciating effect. I know it feels a bit torturous. I don't do these kind of things in the classroom, but just as an example, that you can actually feel the difference between different areas and having same amount of force using different areas, right? So pressure is directly proportional to force. If we increase the amount of force, we're going to have more pressure being generated, and consequently it is inversely proportional to the area. So if we increase the area of the application of a force, then the pressure is reduced. This can be also exemplified in a way that, let's say you have these glass, or you can say, let's just give me let me give you another fun example, right? Let's just say you are walking on a frozen river and you see some cracks, right? What are you supposed to do? Let's say you're standing, right? Are you supposed to run, or what else? If you notice the fact that the force or is going to be the weight of this person or the sticky man, and this is the area, right, which is going to be very small if you keep standing, if you try to run. So you have more chance of breaking this ice and sinking yourself in icy cold water. So it's better to just lie down and crouch or prone yourself, and then simply crawl your way out. That way you will have more area, right? Now the area is greater and the force is again the same, which is the weight of the body. So the force hasn't changed, but the area has increased, so you will have lesser chance of breaking the ice and enjoying the cold icy water swims. You can avoid that by just simply lying down on cracked ice and just crawl your way out slowly and steadily. If you make abrupt moves, then you're going to increase the pressure, because the area would dramatically be reduced by running. So in this case, we can simply say that pressure we can define as force per unit area. And in this terms, since it is force which is going to be newtons and area is going to be in meter square, so we can further say that the units are going to be newton per meter square. That's the unit for pressure, and this is further translated as pascals, right? So we can say 1 Newton meter square is equal to 1 pascals, right? And 1 pascal is a very small amount of pressure. It's not much. We do understand that air has a lot more pressure than this. So we will come to other ideas. We can go into detail of pressure, what types of pressure are there, but I'm just going to keep this topic short for now. What is pressure and what is hydrostatic pressure? Now another idea, which is hydrostatic pressure, or we can say uh, pressure of a liquid. Now you need to understand that pressure is force over area, right? And we do know that uh, for a mass, force would be uh, the weight, right? So that F is equal to W, which is going to be M into G. So I can simply say that for pressure is equal to mg over A. Now that's another way of saying pressure, but that is over an area. Let's just say if we have a cylinder, right, and I fill that cylinder with certain amount of water, right, that's the amount of water. It has a certain height, right, and it has a certain cross-sectional area, and this is the mass, right? So what is the pressure at the bottom? We can simply use a different technique to solve this. Now it is very hard to measure the mass of a liquid, right? But what if I know the density of the liquid, right? So we do know that mass is density into volume, and I can calculate the volume using this. Sorry, I wrote F, should have been A, right? Okay, so we do know that volume is area into height. So I'm just going to replace this M in this formula over here and replace it with these, right? So I'm just going to say pressure of this liquid at the bottom of it, right, which is this surface. I'm just going to highlight it, right? Pressure at the bottom is going to be mass into gravity, which is the force or the weight divided by this. So mass I'm going to replace by rho v, right, over area. And also I do know that v is this, right? So I'm just replacing things around. So rho into area into height. Now over here sorry, I missed g over here, right? The g was already there for mass. So I'm just going to keep g on the other side, right? I forgot this g over here. This g or gravity was also here. So into g and over area. So over here area will be cancelled out. So what you will be left with is rho g h, right? Let me just write it neatly. Okay. So the pressure at the bottom of this fluid is going to be rho into g into h. That means you no more need to concern yourself with the area of this cylinder. It doesn't matter. Let's say if I have another cylinder which is having a little lesser cross-sectional area but has the same height of the fluid, right? And if I try and calculate the pressure at the bottom of it, right, P2, so over here P1 would always be equal to P2. And why is that so? Because this formula is now independent of both the mass, the area, and volume, right? So these things are no more important for you. It's just the density of the fluid, which in this case for both of them the density is going to be same. I'm just going to write mass. So we don't concern ourselves with mass anymore. We have translated that in terms of the density of the fluid and then the height and then the gravitational acceleration, which is pulling this liquid down, which is creating this downward pressure. So over here I'm just going to ask you a question. Let's just say we have a dam wall why the dam walls are made more wider at the bottom, right? This is a water dam, right? This is here's the dam, and why this is made wider at the bottom and very thin at the top, right? Because the greater the height, the more the pressure is going to be on this side, right? So I'm just going to remove this vertical arrow. I'm going to represent the magnitude using the length of these vectors. So you will understand the greater the height, the lesser the pressure is going to be. So the bottom is going to face the most pressure by the water. So hence these dams are created with large areas at the bottom and lesser area on the top, right? So that's one idea how the liquid pressure is going to work. We also call this as head pressure, right? But that term is not used in your book. So just for the sake of information, it's also called head pressure, in which we use this formula only, also known as the pressure of a liquid at the bottom. So that is how you're going to calculate this. I hope I was able to clarify some of the basic concepts. Just go through the exercise available in your book. If you have any queries, just let me know. I'm going to respond to that. And if you have any past paper queries, just post me a picture or just send me a reference number, and I'll try to solve that and put a video for you so that you'll be able to understand how I'm solving those questions. Thank you for your time.